So today I want to talk about the non-LERFness of some groups. Of some mixed three manifolds and arithmetic, hyperbolic, n-manifolds. So maybe let me first talk a little bit about what's LERF. So LERF is something purely about group theory. So if you have a group G, let's assume it's finitely generated. And if we have some group H, subgroup H, and we say it's separable if you take any element not in this H, you can find a finite index subgroup of G, such that this group, the group you choose, lies in K, and this element not in H is not in K. Basically, it means you can find a finite index subgroup separate this G from this H. And I guess, at least for me, this separable group is separable or not, a subgroup is separable or not is very interesting from the low-dimensional topology point of view, because it is related with, if you have a pi1 injective immersed surface in a three-manifold, then whether it can be lifted to an embedding in a finite subcover, and it is related with Ian's proof of the virtual Haken conjecture. And G is called LERF. If a LERF means locally extended residually finite, it's some complicated name. But if it is separable for all the finite generated subgroup, and so there have been a lot of things about LERFness or non-LERFness of some groups, and let's give a very brief review about that. So, of course, there should be more examples, but I will only talk about things kind of related with topology. I guess the first result is the result of Marshall-Hall. He showed that the free groups are LERF. It's back to 1950, 40, something like that. And surface group is proved by Peter Scott in 1978. And also, in the same paper, Scott also showed that it's true for Seyfert's three-manifold group. And then recently, not so recently, it has been a few years, it's for hyperbolic three-manifolds. Okay. So it is, I guess the cusped case is due to Danny Weiss, and the closed case is due to Ian. But actually, there are a lot of things involved in a lot of hyperbolic three-manifold topology, which takes care of the geometrically infinite case. Basically, okay, I will say it later. Say an example. So I guess one of the most one of the example is just if you take, so this is F2 is a two generated, the free group generated by two elements. We know that free group is LERF. But if we just take the direct product of two LERF groups like this, then we get a non-LERF group. Although actually I'm not 100% know about the proof, but anyway. And if you just think about the group of manifolds, basically one-dimensional manifold is Z. It's already here. Surface group is two-dimensional manifold. So if you want to talk about non-LERF group of manifolds, you should start with three-dimensional. And one example is just a graph manifold group. I think it's proved by Niblo and Weiss. Although maybe there was some particular example of graph manifold which was known earlier by maybe Rubinstein and Wang. And there's also one particular thing I want to talk about is a result by Yilu. He showed that, I will not tell you exactly the case, but it is some what I want to say, irreducible non-geometric three-manifold with some hyperbolic piece, and I guess this is usually it's called a mixed manifold. But there's also some condition over there. It's not saying that all such manifolds are LERF, although it's conjecturally they are not LERF. And what you can show is just with some kind of pasting, with some, maybe we call it bad pasting, whatever, of its GSJ pieces. So I will specifically talk more about this part soon. So it is saying that if your three manifold is irreducible, there's some canonical geometric decomposition or GSJ decomposition. They are virtually the same thing. And what Yilu shows was, I give now someone name. Maybe I do not write a name here. Basically, he showed that if you have a certain kind of pasting of the GSJ pieces, then he could show that there's a non-separable subgroup.
So at this point, you've covered all irreducible three-manifolds except Sol.
So actually, Sol is also here, but I can't exactly remember the literature, but actually also Sol.
All geometric.
Yeah, all geometric. Yeah.
I guess non-examples would include non-residually finite groups.
Yeah, sure.
Examples here are all
Yes, they are all residually finite. So maybe I assume our groups I will talk about they are residually finite. So residually finite means the trivial subgroup is separable. Okay. So these are all examples or non-examples in three-dimensional. And if you care about the high-dimensional case, it seems for most of the case, people think about something called, instead of LERF, people care about something called GFERF or QSERF. Some kind of abbreviation of certain things. This is geometrically finite. ERF means the same ERF here. It is for geometrically finite subgroup for high-dimensional Kleinian groups. This is called the quasi-convex subgroup for word hyperbolic groups. And there are a lot of results about this for high-dimensional groups of high-dimensional, say, hyperbolic or non-hyperbolic manifolds. And what I want to talk about today is just some more examples in this non-example category. So M is a mixed manifold. As here, it is an irreducible manifold with a non-trivial GSJ decomposition, and it has at least one hyperbolic piece. That means what we have here. And if one piece is arithmetic hyperbolic three-manifold, maybe for safety reason, I want to write closed here. But actually, I believe I have not 100% sure about detail, but I'm basically 90% sure it also holds for non-closed manifold. If one piece is a hyperbolic three-manifold, there exists a surface subgroup, which is not separable. If one, yeah, at least one. Yeah, there exists surface subgroup which is not separable. Basically, here, if you have a closed manifold, then here you have a closed surface subgroup. If you do not have a closed free manifold, possibly the surface group is just a free group. And so this is kind of, you can compare with this statement, although it's not very explicit. This statement, Ilio's statement, says that if you have some kind of pasting between JSJ pieces, then it's not LERF. And this theorem just says that if you have one particular kind of piece, then it is not LERF. And theorem 2, actually, I'm not 100% about the statement. For any n which is greater or equal to 4, maybe I want to say it in this way, there exists hyperbolic n-manifold with non-separable closed surface subgroup. It seems to say something which is unknown before. And actually, you can add a lot of things here. Actually, the example I have is noncompact and arithmetic, hyperbolic, and manifold. I guess this is the things I actually can add. The words I can add here. And actually, I guess the statement, the proof actually implies many or a good portion of such manifolds are actually non-LERF. So yeah, these two are the main results. Maybe the second one sounds more interesting, but because this is a three-manifold topology seminar. And more importantly, because I do not know much about high-dimensional hyperbolic manifolds. So I will just give you why theorem 1 implies theorem 2. Then we will focus on three-manifold topology. Actually, theorem 1 implies theorem 2. Because of the result of Long and Reed, the double of the pi 1 of the double of figure 8 knot complement embed into the pi 1 of some such manifold, some non-closed, non-compact, arithmetic, hyperbolic, non-compact, arithmetic, hyperbolic, n-manifold.
That's true for all big dimensions?
You mean for all? So here actually you can just replace figure 8 not by any double of any arithmetic hyperbolic three-manifold group. Or maybe here I want to say non-compact, but you know if you have a non-trivial GSJ decomposition, all the hyperbolic pieces are non-compact. But I will definitely use this later. And I guess here, so it is all such arithmetic manifolds, or just a part of?
Well, at least the way that it's stated, it's just some, but probably your argument will be.
Yeah, but because I do not know enough about high-dimensional thing, I will learn about it and try to see that exactly how many of them admit such an embedding. But at least there's such examples. And one more thing I want to say, it is the way we can do this construction here, we definitely have non-compact high-dimensional hyperbolic manifold. Because if you want to do a compact thing, that the fundamental group must not have a Z2 subgroup. But here, the double of some 3 manifold, it definitely has some torus over there, and there's a Z2 subgroup. So here, this construction will always give you some only non-compact manifold. Okay. Oh yeah. By the way, I guess some or many of these examples are over here are GFERF.
Yeah, they're all GFERF by Berger and Hegel.
Okay, I only know some of them, those are rectangled ones. Okay, so let's focus on 3-manifold topology, because that's something that's the most thing I know. So how can we get such non-separable surface subgroup? And this is due to a theorem of E. Lu, which I will just explicitly tell you what is this kind of pasting. So actually, luckily or unluckily or luckily, E. Lu does not explicitly write such a theorem in his paper, but that is, from my point of view, that is the most interesting theorem in his paper, because that is something which you can really work with. If you have M is a non-geometric, is a mixed 3-manifold. And they have, actually, anyway, J1 and J2, there are 2 GSJ pieces. And J1 union J2, oh, maybe their intersection is just 1 torus. And J1 union J2. So this is just a 3-manifold which has a non-trivial GSJ decomposition with only 1 GSJ torus. It is a surface bundle. And so whenever you have a surface bundle, you know it is you can restrict the surface bundle on J1 piece or J2 piece. Each of them is a surface bundle. And you can think about J1, maybe Ji is Si cross an interval, and then quotient by some map. And according to our current setting, they are just J pieces. So this phi is either a periodic map or a pseudo-Nosov map. And they have some canonical form. And the canonical form on the boundary of this surface is a periodic map. And there's a flow line on the surface cross interval, just flow along this interval direction. That gives you some periodic orbit on the boundary of this J1. That will be something called the degeneracy slope. Maybe. Degeneracy slope on T containing boundary of Ji. It's just the periodic orbit. Of the suspension flow on T. And here the condition is the degeneracy slope degeneracy slopes on the torus from the J1 piece and the J2 piece do not match. And then M has a non-separable surface subgroup. So this is a kind of quoted bad pasting means. Just as they so you can, if you just do not have this M, you have just two surface bundles. And if you want to get such a picture, you just do a pasting such that the boundary of the surface are pasted together. So in this way, this J1 union J2 is a surface bundle. And basically, this gives you just half of the elements in the pasting matrix. And you can arrange the other half of the numbers in the pasting matrix to make sure the degeneracy slope do not match.
Just Dean twist along the fibers.
Yeah. So basically, the conditions are this, and degeneracy slopes do not match. These are the two conditions we wanna make sure it happens. If you have a manifold, mixed manifold, you can find a cover such that this picture shows up in that final cover. Then you're happy. You know the original manifold has a non-separable surface subgroup. So we want to apply Liu's theorem to prove this theorem 1. So it needs us to know have some knowledge about the surface bundle structure and the degeneracy slopes in the finite covers. However, it's usually pretty difficult to deal with these degeneracy slopes, at least for me. But actually, if you want to think about something else, it is something is slightly more flexible than the degeneracy slopes. Which is slopes boundary slope of fibered structure. So suppose you have a surface bundle. M is the surface bundle over the circle, and the T is a boundary component. And usually, if you have one such surface bundle structure, actually there are a lot of such structures, as long as first bit number of M is greater than 1. So if you have any S is a fiber surface, then you take S intersect with T. It is just one simple closed curve, or a few copies of this simple closed curve on T. And this gives you a slope on T. Or maybe I want to say, it's actually what I want to call is just a fibered boundary slope, because it is from the boundary of this fibered surface. And basically, the question I want to really study is just if you are given such a surface bundle, or if you are given such a boundary component of a manifold, what are the fibered boundary slope? But actually, we want to really study this question virtually. So the main question is, if you have a map M is a cusped hyperbolic three-manifold, and T is a boundary component, whether there exists a finite cover M prime of M, and then elevation T prime of T. Elevation is just one component of the pre-image of T, such that all the slopes, you can say all simple closed curves on T prime are fibered boundary slope. So I think this question is pretty interesting, not only because of this study of LERFness or NonLERFness of the fundamental group. Personally, I think it's still just pretty interesting by itself, because it shows that for at least in this setting, for this M, it is virtual fibered. And basically, there are a lot of such fibered structures. But if you want to see what is this restriction on the boundary, one boundary component, many of those slopes on T prime are fibered boundary slopes. But it's natural to ask whether all of them are. It is a little bit mysterious, actually. So personally, I believe this question holds for all such M and T, and there's a pretty good reason to believe that, because if this is true, then you can apply E-loose result to all the mixed three-manifold. And you can get a statement saying that for three-manifold, its fundamental group is LERF if and only if it is a geometric three-manifold. which means it supports one of the 8 geometries of certain, one of the 8 certain geometry. Not, oh yeah, maybe I always assume they are irreducible. But currently, I do not know how to show all the slopes are favored boundary slope. But so here are some partial questions, partial answers.
Can you repeat the last thing you said? You said he knows how to show that all slopes are fibered boundary slopes?
No. So this is his conjecture. It's not his conjecture was non-LERF is equivalent with non-geometric. And maybe I want to say this is my conjecture is this question is true. And it implies his conjecture. So here are some partial answers. Actually, here are 2 partial answers. The first partial answer was about a general cusped manifold. I'm T as left. Then there exists some M prime and T prime still as this setting, such that all but finitely many slopes on this T prime are fibered boundary slope. So it's not saying all of them are, but there are only finitely many exceptions. But I guess I cannot call them exceptional slopes because they are already occupied by the Dun filling. All those slopes which give you non-hyperbolic Dun fillings. Okay, so, but
Are the exceptional slopes from, in your sense, something like embedded boundary slopes or like that?
so in what?
The boundary slopes of embedded surfaces?
Oh yeah. Yeah, they're boundary slopes of embedded surfaces. But whether you can just somehow make them to be fibered surface or not, I don't know. But actually, so this is for general cusped hyperbolic three manifold. If you just restrict to the smaller class, if you have M is a cusped, is a arithmetic hyperbolic three manifold, then there exists such M prime and T prime such that all the slopes on the T prime are fibered boundary slope. So arithmetic examples has some connection with number theory, and actually I do not know much about them. If you want to know, you can read. You can ask Alan or read his book. I tried to read his book, and at least I think I understood some of them, but I also forgot some of them. But what I still remember is enough to prove this, give you this partial answer. Okay. So let's forget about this high-dimensional example. So once we have these 2 partial answers, actually we can just prove this theorem 1. So if you have this m prime and t prime such that all the slopes on the t prime are favored boundary slope, then you just use the theory of Thurston about Thurston norm and favored cones. You actually know that one very simple thing you get is just there exist two degeneracy slopes. Maybe I should switch the notation a little bit, because here you have m, here you have m again. Maybe I write this as n. This m is a JSJ piece. Of n. If you can find a finite cover m prime t prime such that all slopes are favored boundary slope, and it implies there are two degeneracy slopes on t prime. Because basically in one single favored cone, it has a unique degeneracy slope. And all those favored boundary slopes have non-zero intersection number with that degeneracy slope. So they're not, so which says degeneracy slope and the favored boundary slope are distinct from each other. And if you use a little bit of maybe point set topology, because all the boundary slopes associated with one single degeneracy slope is actually an open set in the set of all slopes. And actually, there exist two degeneracy slopes on T prime, and they are both associated with one favored boundary slope. And as long as actually you have one, then actually you have more than one. You have infinitely many. Because whenever you have one favored boundary slope associated with these two degeneracy slopes, you just perturb the surface in the favored cones a little bit. You have infinitely many such favored boundary slopes.
Stupid question, but if
Yeah.
the argument is perturb it a little bit, why does that fail if you have all but finitely many?
But if you have only all but finitely many, you do not have two degeneracy slopes. Maybe there's one degeneracy slope, which is one of these exceptional slopes, and it is the degeneracy slope of all the favored cones. Possibly this is true, although I do not really believe it is true, virtually. But this is only what I can show is just you must have all the slopes of favored boundary slope. And then, so here on this M, you have this. This is T prime, no, make it M prime, and T prime. And here is some favored boundary slope. And from here, it is associated with two degeneracy slopes. On the right-hand side, you take another piece over here, and whatever if it is Seifert piece, then basically the theory is pretty simple. All the boundary slopes which are not the regular fiber for the Seifert piece are fibered boundary slopes. Or if it's hyperbolic piece, basically you use the partial answer 1 because there are only finitely many things not fibered boundary slope. If you just perturb this fibered boundary slope a little bit, it will coincide with another fibered boundary slope here. It has another fibered boundary slope, and these two slopes just match.
That's very interesting. Again, but suppose the other piece is a cyclic fibered piece.
Oh, if it's a fibered piece, I guess the degeneracy slope is just the regular fiber. And if you take a slope on the boundary which is not a regular fiber, then suppose that has a lot of boundaries, then that is a fibered boundary slope. Because it bounds the incompressible surface with the other boundary components, and it is definitely not vertical, so it is horizontal. And horizontal means it is transverse with that S1 affiliation, and it give you a fiber structure.
So are you already passing to a big enough cover?
Yeah, I always.
It's fibered and so on.
Yeah, I always pass everything to finite cover. And here is the fibered boundary slope. You just fix one surface bundle structure here, and it has one associated degeneracy slope. But here you have two choices. You can choose one of them here do not match with the degeneracy slope here, and then you get the setting of Elias result. And mismatch of the degeneracy slope. Because here are two choices here. Of degeneracy slope. So here I definitely need all the boundaries, all the slopes are fibered boundary slope to get that. Here are two degeneracy slopes. So degeneracy slopes are pretty rigid in some sense. You cannot, I cannot get a lot of such things.
Maybe you can explain why the arithmetic ones have
Yeah.
all slopes which are fibered.
Yeah. I think in the following 15 minutes, I will try to give some sketch of the proof of these two partial answers. So, okay. So the proof of the partial answer 1 basically use EN's proof that if manifold has reverse fundamental group, then it is virtual fibered. And actually, what EN showed was more than that. Not this again. So here is a theorem, which is I guess the main part is due to En, but it is stated in the following way by Friedel and Viduzzi. I guess maybe if you want really stated in the following way, maybe you should also advise. So if you have IM is a cusped hyperbolic string manifold, And I do not really want to talk about the reverse stuff, so I just restrict to cusped hyperbolic string manifold. And there exists a finite cover M prime of M, such that if you take any alpha less in the H upper 1 of M, maybe real, P star of F less in the closure of a fibered cone. Of M prime. So it says that although the pullback or the lifting of this alpha itself is not given by a surface bundle structure, but it is just it's a limit point of a sequence of fibered structures. I guess what Ian showed was just switch this exist and arbitrary, but just applies Ian's result for finite many times. You can get this result, and this observation is given by Friedel and Viduzzi, and they show that for any manifold satisfying this property, the twisted Alexander polynomial detects the genius. So given this result, the proof of this partial answer 1 is actually just draw a picture, staring at it for a few minutes, and then that's it. I need some colors. So if you have the H upper 1 of M here, and you want to draw its certain norm unit ball, basically I cannot draw much. I only want to draw a two-dimensional picture. So Thurston showed that, okay, Thurston defines some norm on H upper 1 of M and show that the unit ball is just a polyhedron with finitely many faces. And I guess this is the simplest possible picture. Maybe I should not write R2. It's officially in H upper 1 of M. And I should do a little bit of preparation to make sure that all the slopes on T are the boundary slopes. Here, by boundary slope, it means it's a boundary of some surface. Whatever, I do not care whether it's a fibrous surface or not. And this piece can always be done by doing some virtual retract argument for this manifold M with respect to some abelian subgroup. And for this M prime, I still want to draw a certain norm unit ball. And from, I guess, in general, this B1 of this M prime is bigger than this B1 of M. Because otherwise, if you have a non-fibered class here, in M prime, it's still not less boundary of fibered cone. So I should draw a one-dimensional higher picture, and I guess here I can only draw a three-dimensional picture, so like this. So this is your original H1 of M. And here you definitely have some extra dimension here. So maybe it looks like this. If you are having that all the slopes on the torus are boundary slopes, and if you think about all the classes, okay, all the classes which had certain slope on T, then it is a codimension 1 subspace here going through the origin. This is all the classes with 1 fixed boundary slope on T. And if you pass to M prime, it is still a codimension 1 subspace. But if it's a 3-dimensional space, then this is actually a plane. And the plane goes through exactly these 2 intersection points. So it should go through these 2 points. And this picture tells you that this plane in this picture actually does not contain this white piece. So it must be some plane look maybe like this. I'm not good at drawing this, but it more or less looks like this. And if you look at, say, the neighborhood of this intersection point, this theorem just tells you that this point lies in the closure of a fibered cone. So it means either this face is a fibered face, or one of these two faces are fibered face. So maybe this is this one. Then you just take any point around here. This point, maybe I should not use yellow. This point is actually a fibered class. And this shows that this slope you are thinking about is a fibered boundary slope. So this is a kind of a generic picture, or for a generic slope on the torus, you have such a picture. And the non-generic case is just if your slope, you choose a slope such that the classes with this slope is just maybe this line or this line. Actually, this gives you the kind of the exceptional slopes. Because if you look like the slope you choose look like this, then possibly it's not definitely true, but it's possible that the plane here is just given by, say, this plane. Look like this. Okay, it's not a very good picture, but it's just its intersection with this boundary of this unit ball is just lies in its codimension 1 skeleton. And if this happens, then there's not a fibered class in this purple plane, and it means possibly there's not a fibered class in this M prime with this slope as its boundary. So basically, it's just of course, in the real picture might be here it is already 100 dimensional, and here maybe this is 1,000 dimension, but this is more or less what the picture.
If the original thing is 2-dimensional, and the stuff that goes through the vertices is 1-dimensional.
Yeah.
Right, it's 4-dimensional projectable. But if you start out 1,000-dimensional, then what are the things that end up bad over there?
So basically, it's still you do not think about the dimension, you just think about the codimension.
Okay, yes.
So still, say here is the B1 is 1,000. This unit ball, the boundary of this unit ball is, okay, 1,000 is too much. It's n. The boundary is of dimension n-1. And the kind of the singular part, like this, is a codimension 2. But in this here, it is it's more or less the same. And here, if you take a plane, it kind of takes a cone over the singular part, so it's still a coordination one thing. Okay, 3 minutes for the partial answer 2. So still, arithmetic hyperbolic three-manifold. Okay, for a really long time, it is a mysterious word for me. And maybe it's still now. But if you just restrict to non-compact case, it is slightly less mysterious. Because non-compact hyperbolic three-manifold, means its group is pi1 is commensurable with PSL2 of OD.
Arithmetic.
Oh yeah, arithmetic, yeah. It's pi1 is commensurable with PSF OD. Here, OD is just the algebraic integers in the Q adjoint with negative of D. Of course, here, yeah. So it's at least, basically, in some sense, it's fundamental group. And commensurable means you can take a correct conjugate of this pi1 in the isometric group of H3 such that the intersection of these two guys is a finite index subgroup of each of them. And the important property I will use, basically this is one of very few properties I know, is just the commensurator of this pi1, which is defined to be G less in PSL2C, such that G pi1, G inverse intersects intersects pi1, has finite index in both of these two guys. It's exactly PSL2 of this field.
PGL.
Or PGL, yeah.
PSL is still discrete. No, it's not.
If I read here, I read PSL, then that should be PSL.
No.
Whatever.
You want GL because otherwise it's not the full concept, right?
Okay. Yeah, maybe here I should also PGL, right? Yes, no. Whatever. Okay, this is more or less one of the very few things I know, but this tells us H3 mod this G pi 1, this intersection at first, because it is has finite index in this pi 1, so it is a finite volume hyperbolic three-manifold, and it covers your original manifold H3 mod pi 1 by two ways. And both of them are kind of obviously. One way is just map. If you take any point in H3, it's just map to itself. But another way of the cover is just H3. You conjugate this group by pi 1 intersect with G inverse pi G. And it is, I guess, x mapped to G inverse of x. And this is actually a homeomorphism. And then here you still do the same thing. And this picture definitely not commute. So this gives you that this manifold covers the original manifold by definitely 2 different ways. And if you take this G, it's a very simple matrix. X less in Q square root minus D minus Q. Then this G actually just do some kind of rotation on the slopes of the torus here associated with infinity. And if you just choose this x such that its argument is really small, then it moves one of these exceptional slopes into the open interval, which are non-exceptional slopes. It moves the exceptional slope. Okay, I to the non-exceptional slope. So if you have an exceptional slope here, if you pull it back here, it is a possibly exceptional slope. But if you look at its image here, you'll find it's actually an unexceptional slope. Basically, this is the proof of the partial answer 2. And I think that's all. Thank you.